Hello and welcome to the session 4 of FIR filter design. In this session, we will look at the FIR filter design methods and the window functions. So there are three types of FIR filter designs: a Fourier series approach, FIR filter design using window functions, and a DFT method or frequency sampling method. We are going to solve the problems based on Fourier series and primarily the window-based functions. So to start with a Fourier series method, in the previous session we have seen four different types of FIR filters: type 1, type 2, type 3 and type 4, depending upon the type of symmetry between the impulse response coefficients, that is positive symmetry or negative symmetry, and then whether the length of the filter is even or odd. So the linear phase condition of FIR filter is h of n plus minus h of n minus 1 minus small n, where capital N, it represents the length of the filter and n minus 1 represents the filter order. Now the Fourier series representation means hd of omega or hd of e raised to j omega is equal to summation n equal to minus to plus infinity hdn into e raised to minus j omega n, where hd of n represents the impulse response or the filter coefficients as a Fourier coefficients, and hd of omega, it represents the frequency response of the filter. So in the Fourier series method, hd of n, that is the filter coefficients, they are computed by applying the inverse discrete time Fourier transform on hd of e raised to j omega. So this formula is 1 upon 2 pi integration from minus to plus pi, because we are taking only one cycle, that is a 2 pi cycle, 0 to 2 pi or minus pi to plus pi, within which there are the primary set of frequency components for a system, for a filter. So under the integration, hd of e raised to j omega into the basis function e raised to plus j omega n d omega. And this is for the range of small n from minus to plus infinity. Now in the taking the case of an ideal low pass filter. So in case of the ideal low pass filter, we could see here the pass band is available from 0 up to the cutoff frequency omega c, and beyond omega c till pi it is a stop band, and again from pi to the 2 pi minus omega c is the value here as the cutoff frequency, where this pass band basically is the replica of the pass band available between 0 to omega c. So the magnitude response mathematically will be expressed as h of omega. The mod of h of omega is equal to 1. The magnitude is unity. For mod omega range between 0 to omega c, that is the pass band, and it is 0 for omega c till pi, that is the stop band. Now in order to obtain the impulse response h of n, an unknown, we are going to apply the inverse discrete time Fourier transform as stated in the previous slide, and by doing that we will get h of n as sine of omega c n upon pi n when n is not equal to 0, and at n equal to 0 it will appear as omega c by pi. So this step needs to be solved in order to obtain this impulse response as denoted here for low pass filter. Similarly, for the high pass filter case, the magnitude response is mathematically expressed as it is having a magnitude of unity, that is the pass band, from omega c to pi. Now from pi onwards, this part is the replica of the previous pass band. So we are considering only this pass band herewith. And during the integration, this entire cycle will be taken care. And beyond that, there is a stop band for high pass filter, since it is passing the high frequencies and attenuating the low frequencies. So again, by applying the inverse discrete time Fourier transform to this description, we get the impulse response as sine omega c n upon pi n, it's a negative sign, and is 1 minus omega c by pi for n equal to 0. So this needs to be solved to confirm the impulse response terms. Next is the bandpass filter. As in case of the bandpass filter, there will be two cutoff frequencies which will be deciding the boundaries for passband and stop band. So we could see that in between 0 to omega c1 there is a passband, in between omega c1 to c2 is the stop band, and so on. For omega c2 beyond is again the pass band for the band pass filter. And when we apply to this mathematical description by substituting the different cutoff frequency values in the range of this 0 to pi and solve for the inverse discrete time Fourier transform, we obtain the impulse response for n equal to 0 and for n not equal to 0, these two terms. And lastly, for the band stop filter, we have to look at how the impulse response can be obtained by applying the inverse discrete time Fourier transform for the magnitude response of the band stop filter in the same way as we did for the previous three cases. So this is a summary in terms of the frequency, the ideal filter frequency responses for low pass, high pass, band pass and band stop, along with the impulse response result for each case when we apply the inverse discrete time Fourier transform to the respective frequency responses.